Okay, so here's the review of problem set 3. So the first question is to find the total weights of the graph. So we need to add up all the numbers on this graph, and we need to add up all the numbers on this graph. So for this graph, we've got 12, 2, 7, 6, 5, 4, 3, 11, and 10. Adding that up, 4, 13, 9, 4, 8, 21, no, 22. 22 plus 8 is 30. 1, 2, 3. So that is a total weight of 60. So for graph A, the total weight is 60. For graph B, we're going to call this graph A. We'll call this graph B. For this graph, we've got 9, 10, 14, 19, 22, 30, 32, 38, 45. So 60 and 45. For the first graph, find the weight of a Hamilton path that begins at A and ends at C. So a Hamilton path means every vertex, it starts at A, ends at C. So we're going to go to D, E, B, nope. We're going to go A, B, E, D, F, C. So I went A, B, E, D, F, C. A to B was 10. B to E was 4. E to D was 3. D to F is 7. F to C is 6. So 10, 14, 17, 24, 30. There are others. I found this one. For the second graph, find the weight of a Hamilton path that begins at E and ends at C. I'm going to erase all these tick marks that I made so I can see them well. So I want to start at E and end at C. So 5, 1, so 6, 14, 24. So I went E, D, A, B, C, and the weight is 24. For the graph below, we want a whole bunch of finds. Now, oh, come on. Find a Hamilton cycle that starts and ends at vertex A. Calculate the weight of the cycle. I'm just going to go ahead and I'm going to take the easy way out. So I went A, E, D, C, B, A. And then that is 26 plus 101 plus 93 plus 10 plus 15. I'm not even that talented to do that in my head. 26 plus 101 plus 93 plus 10 plus 15. That's 245. Now, you might have found a different one. That's okay. Find a Hamilton cycle of less weight. List the cycle and the weight. So I want to find one that weighs less than that. So I want to find one that has a smaller amount to the edges than 245. Now, you may not have, you may have found the cheapest one, the one of least weight already. So just find a different one if that's the case. I'm going to guess that edge 10 needs to be in there, and edge 13 needs to be in there. I'm gonna, out of the choices that I have 101, 403, or 26. I am gonna take 26. And I have no choice but to now go up to D, and then back to C. I don't know if that was any less weight or not. But we'll find out. So I'm just going to start and stop at A. I went A to E, B, C, D, back to A. A to E was 26, plus 13, plus 10, plus 93, plus 86. Wait, 26, 13, 10, 93, 86. Okay. That looked weird to me. I'm pretty sure it's less. 26 plus 13 plus 10 plus 93. Let's say 86. Yep, 228. That's less. Okay, find a Hamilton cycle of more weight. List the cycle and the weight. Well, I want to ensure that I have more weight, so I'm going to make sure I pick edge 403 and then work from there. Go up to 101. I can't go to 93, but 62 seems fun. Come across to 15 and up to 17. By having 403 in there, I already know I've got more weight. So we'll start with A again. A, C, E, D, B, A. And that was 17, 403, 101, 62, and 15. So 17 plus 403 plus 101 plus 62 plus 15. Now, later on, so that was 598. Later on, you're going to learn how to maximize and minimize these paths using an algorithm, which is a measured set of steps that you got to take. So in number 3, we want to explain why there exists a Hamilton path but not a Hamilton cycle. When I'm explaining that a Hamilton cycle exists, I can just show it. My path. My Hamilton path is vertex F, B, A, E, C, D, G. Now, why does it not have a Hamilton cycle? Well, I have bridges. No Hamilton cycle. Two bridges. Now remember, Hamilton cycles are every vertex. Every vertex. So if I have a vertex of degree 1, it can't be a cycle because I'm only going into that vertex and I can't go out of that vertex, so it kills the cycle. In this graph, explain why there does not exist a Hamilton path nor a Hamilton cycle. Well, in order for it to be a Hamilton path, the edges going to vertex A would have to be in it, and the edges going to vertex C would have to be in it. Whether it be a Hamilton path or a cycle, I have to get to vertex C and I have to get out of it. And I can't just stop and start at vertex C or vertex A because I have the vertices of degree 1. So, no Hamilton path or cycle because vertices of degree 1, the graph has vertices of degree 1 and the vertices of degree 2 make their own cycle. Okay? So I'm pretty sure that you guys can find these. I'm not going to go over them. I believe in you. I believe that you can find them. But I want to explain why that the graph has no Hamilton path that starts at B. If I started a Hamilton path at B, I would have to repeat B. I go up to A, around, down. Oh, look. Same with C, okay? Can't have a Hamilton path that starts at B or C because you will repeat vertices. Okay? Explain why the graph has no Hamilton cycle. If a graph has a bridge, it doesn't have a Hamilton cycle because you don't have an in and an out for the vertices that are making the bridge. Okay? Whoops. All right, next one. Oh, these are fun. So we need to find a Hamilton path in a cycle. I'm just going to go ahead and indicate the cycle because you get the path from the cycle. You will need this Hamilton cycle later for origami. So make sure you write it down. Now I'm doing this and making sure I leave myself a way out. I screwed up. I screwed up. See, even I'm not perfect. It's okay to make mistakes, and I guarantee you that I'm not editing this out. I can 100% assure you of that I will not be editing this mistake out. Because I think it is, I might edit that horn out, though. I live on a main street in a very busy city. Let's try this again with a bigger line. There we go. So save that. You're going to need it. All right, and if I was to do the Hamilton path, there's my Hamilton path, but I'm not. This is actually a graph of a dodecahedron. For the nerds amongst us, that is a D12. Okay? I heard one Dungeons and Dragons nerd giggling in the background, just in my own mind at least. This is an icosahedron, which for the nerds amongst us is actually a D20. So let's find the Hamilton cycle in the D20. And there are others. I'm just really good at finding these. Okay? So if you have one that doesn't match, that's fine, but make sure you save this one. Okay? You're going to need it. Now, the following graphs are Hamiltonian. Find the Hamilton cycle or the Hamilton path. Easy peasy. And of course, I'm sure you're saying, sure, Gendron, easy for you. And I understand that this is easy for me. But if you fumble around enough, you will find these paths or these cycles. So I'm not going to go through these, but I am going to talk about problem 8. This is why I gave you the Knight's Tour example. The first step in these is to assume there is a Hamilton cycle. That means all vertices of degree 2 have to be in this cycle. I'm going to use a yellow. We're going to use a pretty yellow color, and I'm going to up the game a little bit. Line thickness is 5. So that means these guys are all in there. But that also means that these guys are all in there too. However, we now have the vertices making their own cycle, so this cannot be a Hamilton cycle. Therefore, this is the fancy math symbol for therefore, no Hamilton cycle. Same goes for the one below it. Okay? Here, all of these vertices of degree 2 make their own cycle. But you're going to say, but Gendron, didn't you use that picture in the graph in the last one? No, I didn't. As you can see, it's bigger. Why are you doing that thing? Stop doing that thing. This one's disconnected, so no Hamilton cycle. You have the bridge here, also vertices of degree 1. By the way, you can find Hamilton paths in some of these. But that's not what I'm looking for. I want to know specifically why these do not have Hamilton cycles. You're going to find this pattern showing up a lot. In my in-person classes, we call these bow tie points. You won't hear that outside of our class. It's not official math language. But they all seem to come down to a point to make a bow tie. But so that's why we call them bow tie points. But what really is happening here is the vertices of degree 2 make their own cycle. So no Hamilton cycle there. This guy skip. It's hard. If you want to do it for a bonus, sure. But it is an exhaustive proof, which means you highlight all the vertices of degree 2 and then have to keep going from there because they don't really tell you much. What you have to do is you have to go through and go, well, I could go here and here and here and here and here and here, and then vertices will be repeated or ignored, and you have to do that for every possibility. So for the ambitious among us, go for it. But don't sweat over that problem. You won't see it again. But what you will see is this bow tie point. These bow tie points. What's happening here is that the vertices of degree 2 make their own cycle. That's actually a bow tie point. If you flip down the triangle EFD below it, you would see that. So now let's look at these questions. If a graph is classified as a tree, does it have a Hamilton cycle? Here's a graph that's a tree. Does it have a Hamilton cycle? No. Trees are bridges. Trees are bridges. If you have more than 2 vertices of degree 1, is it possible for the graph to be Hamiltonian? No. because you will end up backtracking and repeating. Yes, it does. And we actually, I'm responding to if a graph is classified as complete, does it have a Hamilton cycle? Yes, it does, and we have a formula to figure it out. Every complete graph will have a Hamilton cycle. Every complete graph, n greater than or equal to 3, has a Hamilton cycle. I'm saying n equals greater to 3 because this is K2 right here, and it clearly doesn't have a Hamilton cycle. It has a Hamilton path, but no cycle. If a graph is a wheel, does it have a Hamilton cycle? I'm going to draw a wheel graph right here. Yes, it has a Hamilton cycle. Wheels always will have Hamilton cycles. All bipartite graphs are Hamiltonian. Now, I got an email before the recording of this asking about bipartite graphs. I am going to remind you what a bipartite graph is. This is for you. You know who you are. I got you. So, bipartite graphs are Hamiltonian. So, a counterexample means something that makes this not true. So, here's a bipartite graph. A bipartite graph is a kind of graph that I can split the vertices in two groups. If vertex A is in group 1, neither vertex B or vertex C can be in group 1. So vertex B will be in group 2. Vertex C is in group 3. This is not a bipartite graph because it's 3 groups. Okay? Not a bipartite graph because it is 3 groups. Here is an even cycle. It is bipartite because it is only 2 groups. Here is a tree graph. Tree graphs are all bipartite. Here is your counterexample. It is a bipartite graph, and it does not have a Hamiltonian cycle or Hamiltonian path. Hopefully that helps with that review. Like I said, you will not get a quiz until after problem set 4. Okay? So good luck, and stay tuned for more.